Welcome learners. Today we are going to start our module 3 in week 1. Before I start today's topic, let us first recollect what we have learned in our last module. So we have seen a very interesting and popular approach of solving problems which is known as check and guess method. In this method, every time you first guess a particular solution and then you check whether the solution is correct or not. If it is correct, then you will stop the algorithm. If it is not correct, then you need to update the previous guess so that the new guess will be more accurate or more correct. Now you need to apply certain innovative strategy to update the guess. Now today what we will be doing is that we will actually analyze the Babylonian search algorithm, the algorithmic steps, and we will see some more implementation issues while executing the algorithm in digital computer. Okay, so let's start then. Let us first write down the algorithm which we have learned in our last lecture, Babylonian search method. Here in this table I have mentioned 3 columns: step number, instruction and properties. Here properties means the 5 different properties which algorithm must satisfy. So we will see how this particular algorithm satisfies all of them, okay, during its progression. Now what is step 1? So you need to read the number n for which the square root we need to find out. Then you need to guess the value of x. And then what was the principle? If you remember, you will check if this guess is correct, otherwise you will update. So how do you check whether it is correct or not? If it is a correct guess, then value of x square will be equals to your n. So as long as value of x square is not equals to n, you need to repeatedly update it, right? So therefore statement 3, repeat step 4 until x square minus n is not equals to 0. So this step 4 means this is what the update statement. So until this equation violates, continuously update using the step 4, right? Now once this equation violates, that means what? X becomes square root of n, then this step 4 will not be executed. It will directly jump to step 5 and print the value of x, because the moment it actually violates this equation, that means now x square minus n will equal to 0. So when no longer update is required, we will skip this part and jump up to here. From here we'll straightway jump here and print x, and the value of x is nothing but your square root. Now let us closely look to this step 4. We need to understand this kind of a statement to further analyze the algorithm. If you look this particular statement, update statement, it is something like an equation in mathematics. Is it really an equation? Let us see it little detail. Okay, so let's take the step 4. So I have given a similar kind of example, x equals to x plus 2. This is simpler updation expression. Okay, now let us investigate this statement. Interestingly, if you think this is an equation, then you can cancel this x from the both side, then it will immediately become 0 equals to 2. So in mathematics this is an invalid equation, right? So we say in mathematics this is an invalid equation because 0 cannot be 2. But on the other hand, in programming this is a valid update statement. That means when I am writing this statement in programming, this is not exactly has the same meaning as we have the meaning of equation in mathematics. Okay, now let us see what happens actually in the circuit. To understand it, let's say we have a variable x which is equals to 5, and now we want to execute this statement. Okay, so when I say x equals to 5, that means what? We have a memory cell of name x and that contain the value 5. This is what the meaning of x equals to 5. Now then we are executing this operation x equals to x plus 2, and this is in computer, this is known as it's an assignment operation. What it does actually, it executes the right hand side first, and whatever value it has, it will reassign that value to the left hand side variable. So if that is the case, then x plus 2 means what? What is the value of x currently? So current value, this is current value, current x, that means current x is 5. So 5 plus 2 equals to 7. Now this 7 will go and be assigned to x, which is the new value of x, right? So this right hand side will be executed first. Where it will be executed? There is a separate register or memory location which is known as accumulator. So in this accumulator, this right hand side will be executed first. So how it will be executed? X plus 2. So x will be fetched from here plus this 2. This will become 7. Now this 7 will go back and reassign to this 5. So now this 5 will be replaced by 7. This is what the meaning of this statement x equals to x plus 2. So it's not a mere equation which we normally used in mathematics. So then what kind of statement this is? If you want to see, then x plus 2 is mathematically equivalent to the statement like this. In the numerical analysis and lots of places in mathematics, we write this kind of equation. What is the meaning of this equation? The value of x in ith iteration plus 2 will be the value of x in I plus 1th iteration. And the same thing is in computer. When you want to execute this statement, you should write this. What is the advantage of writing this statement? If you notice, in this particular statement, the right hand side statement RHS, let's say I am giving the name R2, and this statement, let's say this is R1 statement, this is R2 statement. So, in this R2 statement, we need two variables. Even though conceptually they are same variable, xi and xi plus 1 are basically two different instance of the same variable. We are seeing the value of x in two different time, right? But actually conceptually they are same variable, but since the symbols are quite different, then if we write this statement, we need two different variables. But if you write this statement, see, even though it has the same meaning, but while programming we need a single variable. Now since the right hand side will be executed first, so the current value will be added by 2 and then it will be assigned to the left hand side, so it will generate the new value of x. So with the help of a single variable, we are achieving these mathematical assignment in program. Now let's have our focus on step 3, and in step 3 we are actually calculating this thing, right? What we are actually doing, every time we are calculating x square minus n, and we are checking whether that is equals to 0 or not. If it is 0, then we stop the algorithm and print the value of x. If it is not, then we again update the value of x. Now we will repeat these steps again and again. Now if you see here, we are actually comparing two real number for equality here. This is one real number, this is another one. We are actually matching, right? Finding the matching, exact matching between these two numbers. Unfortunately, exact matching between two real numbers is impossible in numerical computation. Now let us try to understand why it is so. Now, as you might have guessed, that computer uses fixed number of bits to store any number. So however powerful computer you use, it will always have a finite number of register because it's a finite size device. And if you see the real number, this is a set, okay? The cardinality of this set is infinity. That means what? Even if you consider two different real number 1 and 2, you will get infinite number of real number in between this. So when you try to map this real number set into your digital machine, you will not be able to do it fully because this is the real number is the infinitely large set, whereas your digital machine can only accommodate some fixed number of numbers. So there is some mechanisms. So let us see how to handle this situation. Let's say we have a number 1, 2, 4, 5, 6, 7, 8, let's say. And let us also consider we are actually working in a machine where the machine can only support 1, 2, 3, 4, 5, let's say this many number of 1, 2, 3, 4, 5, 6 bits, okay? Then we start writing this number 1.45667. Now see, we do not have the available space to accommodate this 8. So then what will happen? We will do some kind of round off and we will approximate this value to the nearest value. So there are certain rules to do the round off. So this number, how do you do the round off? Since it is more than 5, so we will discard this and we will add here plus 1. So your number will become, let's say this is what your register 1, 2, 3, 4, 5. So 1.456 and this will become 8. Okay. Now, so that means you are adding some error here. What is the amount of error? If you subtract, then you will get 0, 0, 0, 0, 2. See, the error is very small, but please you need to remember that you are doing this kind of operation millions and millions of times in a computation. So if you accumulate all these errors large many times, then that aggregated error might be very large, and in some cases it may give you a complete different result, incorrect result. And therefore this round of error is a crucial issue in any kind of computation whenever the computation is executing inside a digital machine. Now therefore in some situation it may even so happen that because of the round of error the entire calculation is wrong and the project failed. There are several examples there. Okay, large projects are getting scrapped because of this round of error. So there are many ways to reduce this round of error, and those things are beyond the discussion of this topic. But one thing that is for sure is that if you are dealing with a real number, you can reduce round of error, but you cannot fully ignore it because anyway it will come, right? Now, so let us see what is the impact of this kind of round up method in our example. So let's start with the example, right? So here what we have chosen n equals to 20 because our objective is to find out the square root of 20. So and we are assuming the computer which I am using, it can perform 3 digits up to 3 digits calculation after decimal points. Okay. So now in iteration 1, the value of initial value x is 5, that was we have already told. So n by x is 4 and this value is 4.5. Now we are checking x square which is 25. Okay, and x square minus n which is 5. So this is not equals to 0. So therefore we will update. So what value we will update? This value will be the new value of x. So in iteration 2, this 4.5 will be treated as a new value of x. Now again, for this x we need to calculate n by x. What is n by x? This is 4.444 dot dot dot. It will go, it's a never ending number. So therefore you cannot fit this particular number in a finite device. So since our machine actually supports 3 digits after decimal point, so we will round it off by this number. Okay, so see here the error comes in. Now in the next phase we will add these two and divide and take an average. So the error which we have incurred here, that will again propagate to the next calculation, because we will use this approximate value to the further calculation, so that error will continuously be there. So if we take an average of these two numbers, this will come like this. Again, this is a never ending number, and since your machine only supports 3-digit number, you will actually round it off up to 3 decimal digit. Now we calculate this 4.5 square and we are getting 20.25. Now the difference between x square minus n modulus is 0.25, which is still not equals to 0. But see one thing, this error, this is if it is E1, this E2, see E2 is less than your E1. Now since this is not equals to 0, we need to again update. How do you update it in iteration 3? This value will be there x in the next iteration. Now similarly we calculate n by x for this x, and we are getting a very large number. Since we have only 3 bits, so we actually do the round off. Now see, when you do this round off, your x and n by x becomes the same, right? And actually what happens, if your x and x by x becomes the same, then if your average also will become the same, right? Now your, what is the x square? X square is this much. So the error right now, x square minus n, that means 20 minus this quantity, is less. But still this is not equals to 0, and you can see it is E3. Now the point is, what you should do according to your algorithm, since it is not equals to 0, you need to re-update. How do you re-update? You will take this value in 4th iteration and you will re-update. But surprisingly, your earlier value was 4.472, now also 4.472, so nothing will change anymore, because this will also 4.472, this will also 4.72, and this is also the same value, and you have the same error. Now the thing is that we got stuck here. Even though this is not equals to 0, but when we are going to update, we cannot update because we are not getting any better value. The same value we are getting again and again. So no improvement is happening, but still there is some gap between the x square and 20. So what does it mean? It means this will run, the algorithm will run forever, because it will not going to stop, because every time you will get the same difference. But what is the logic we have written? X square, we have written the logic like x square minus n equals to 0, then only we should stop this. Since because of this phenomenon we cannot satisfy this equation in this system, so it will be never stopped in this system and it will go forever. It's an infinite loop or infinite progression of the algorithm, right? And that is what we need to restrict, because finiteness is one of the property of every algorithm. But why it has happened? Because of the round of error, some error creeps in and we cannot represent the data anymore. If we would have allowed further more digits, then you would have seen that these values are actually not same, they are quite different. Instead of 3, a powerful machine might have, let's say, 50 bits, okay? Now after these 50 bits, the same phenomena will anyway happen. So this kind of thing will happen. So it is easy to understand in a 3-bit machine, but for a larger specification machine, this error will again happen. But see the interesting part, the difference is not that much. Here the aggregated difference is not that much. Now we can realize this has a root But because of this equality condition, my algorithm is not going to be terminated. That is the problem. And what is interesting is every iteration, your E1, E2, E3, it is actually a converging sequence. It's monotonically decreased. Of course, it is infinite loop right now, but still it suggests that it has an answer. So the mathematically it is correct, but because of the computation issue, we are in an endless loop. So we need to rectify this problem. To rectify this problem, let us suggest something. So what we will do, we will not write this expression. Instead of that, we will replace this by this expression. What does it mean? This means whenever this quantity is very close to 0, is delta, that how close it is, that depends on your delta. It is very small number. So what we are saying, let's say this is what your 0, and you take two boundaries. This is minus delta and this is plus delta. Let's say for the time being, value of delta equals to 0.0001, and here the value will be minus 0.0001. So from minus 0.001 to plus 0.001, every number will be treated as 0. That means whenever this condition will satisfy, we will treat that it reaches to the root. Again, it's an approximate, but it is very close to that root. If you need even closer, then what you need to do, you need to make this delta value even smaller. Let's say next time you are choosing 501, that means now you are reducing this and you want to be more accurate, more closer to the 0. Now you cannot get to the exact 0 that I have already shown, because there are infinite length number which cannot be accommodated, so that ideal 0 will never get it up, right? So we will write it in a little different way, more mathematical way. Modulus of x square minus n is less than equals to epsilon. This statement could be written like this. Now in our algorithm, what we have written, until this condition satisfied. So instead of equal to, let us see this inequality, and this inequality could be written as the reverse one, x square minus n modulus greater than delta. Now we can avoid that issue which just now we have discussed. So now we will not find out the exact matching between two numbers, rather we will add some tolerance and we will say if the number lies between these range, then we will treat them as 0. So in that way we can actually make that endless loop to a finite loop. Let us see what happens. Now see, now I am changing it and I am writing until modulus x square. Let me rough it up. So I am writing that modulus x square minus n greater than delta. Now the question is, who will provide the delta? The programmer will provide the delta. The amount of accuracy that you need, that will be supplied by the programmer, and accordingly this will be calculated. So we need to change this line and make it read the initial guess of x and delta. That means supply the delta as well, right? So now this algorithm is complete, and let us see what are the characteristics or properties of algorithm has. Okay, so let's see this. First we need what? Input. What are the properties? Input, output, and then finiteness, then definiteness, and then your effectiveness. These are the various property of algorithm. Let's see, all these property are there in this algorithm or not. So if you see input here, input property should be, every algorithm should have either 0 or more input, right? In this case, how many input we have? N, x and delta. So these are the input, right? So input is there. Now let's see where is the output. Every algorithm needs at least one or more output. Okay, this plus means one or more. Okay, so therefore here x is the output, so it has one output. Then the finiteness property. What is finiteness property? See here, earlier it was infinite, but now because of applying this delta, now the program must be terminated. right? Let's say we have chosen delta equals to 0.0001, and what we receive, x square minus n modulus value is equals to 0.000012. Now what it means? So this value is in between minus 0.0001 to 0.00001, in this range, right? In this closed interval you will get this. So that means we can treat them as a zero. Approximately it is so close to zero, then we will call it a zero. But let's say if you choose delta is 401, then this is, you cannot actually stop here, because this number is beyond this range, outside this range. So you need to go, you need to further update the x, and you need to wait for the difference. When the difference will become less than this one or inside this region, then only you will stop your algorithm. In that way you can increase your accuracy part. So therefore, because of this delta, our algorithm becomes finite. Earlier it was infinite. And the property definiteness, that means every step is unambiguous. Here you can see everything is unambiguous. No ambiguity you can find here. And another is effectiveness, that means every steps are basic and simple. That also it is quite obvious here. Every step you can understand in plain English and anyone can proceed, right? So what we have seen, all the 5 different properties of algorithms are completely established in this Babylonian search method. So this is what our, this 1 2 3 4 5, all these steps are finally becomes your correct algorithm for Babylonian search. So we have discussed mostly all issues of this algorithm. So with this we are actually ending the module 3 here. Before we leave, let us summarize what are the content that we have learned as of now in this module. So first of all, we have learned that round of error is inherent in any numerical computation. You cannot avoid that, and your round of error may be accumulated to a very high amount of error, and finally your final result may be completely incorrect. So we should be very careful about that. Before we start the computation, we may need to use some intelligent way so that we can compute in such a manner that the round of error will actually be minimum. Okay, and then we have learned all the different 5 properties which every algorithm should satisfy, like input, output, then finiteness, definiteness, and then effectiveness, etc. So I hope you have enjoyed this discussion. So we will meet again in the next class. Till then, happy learning. Thank you.